In this video, we're going to practice the method of trigonometric substitution for evaluating integrals that include expressions of these forms. The square root of a constant squared minus the variable squared, the square root of a constant squared plus the variable squared, and the square root of the variable squared minus a constant squared. In each of these cases, we're going to substitute a trig function for our variable, resulting in a trigonometric integral that we can then simplify and evaluate. Anytime we have the expression the constant squared minus the variable squared, we're going to substitute in the constant times sine theta. When we have the variable squared plus the constant squared, we will substitute in the constant times tangent theta. And finally, when we have the variable squared minus the constant squared, we will substitute in the constant times secant theta. As we go through the problems, we'll see how each of these will work out. Let's look at number 1. Looking inside the root, we notice that we have 5 squared minus x squared. And that's of the form a squared minus u squared. So we're going to start off by substituting 5 sine theta for x. Next, we find dx. Now, before we continue with our substitution, let's draw a right triangle with the acute angle theta and identify each of the sides. Because we have that 5 sine theta is equal to x, that means sine theta is equal to x over 5. And we know that sine is the opposite length over the hypotenuse. Now, we could use the Pythagorean theorem to see that if we take this leg here, let's call it y for a moment, that would be y squared plus x squared equals 25, leaving us with y equaling the square root of 25 minus x squared. And you'll notice this radical expression is in our integrand. So because that's the leg adjacent to theta and we have a hypotenuse of 5, we know that the cosine of theta is equal to this square root over the hypotenuse. In other words, the square root 25 minus x squared is equal to 5 cosine theta. Now we're ready to do our substitution. In the numerator, we have our dx equals 5 cosine theta, d theta. In the denominator, we have x squared, so we're going to square our 5 sine theta to give us 25 sine squared theta. And then we also have our square root of 25 minus x squared, which we see below is equal to 5 cosine theta. Cancel. Let's put the 1 over 25 on the outside. We have 1 over sine squared, which is the same as cosecant squared theta. The antiderivative of cosecant squared is a negative cotan theta plus c. And now we'll replace cotan theta with an equivalent expression involving x's. Well, if we look at our triangle, we know that the cotangent of theta is equal to the adjacent side, which in this case is 25 minus x squared, over the opposite side, which is just x. So we end up with negative square root 25 minus x squared over x. We have that 25 in the denominator plus c. Now you're going to go ahead and do number 2 on your own. First of all, notice that inside the radical, you've got a constant squared, 1 squared, but then you also have a variable squared, but this one isn't as straightforward as number 1. Right here, we have 4x squared. So we could start off with a u sub, allowing u equaling 2x. That means that du is equal to 2 dx. And of course, half a du is dx. If we substitute this first, we're going to have 1/2 the integral 1 minus u squared under the root du. Now you have your constant squared minus your variable squared, and you can go ahead and you can use the substitution at the top of the screen, a squared minus u squared, where u is going to be a sine theta. Go ahead and do number 2 now. Number 3, the integral from 0 to 2 of x cubed times the square root of x squared plus 4 dx. So first we notice inside the square root, we have our variable squared plus a constant squared, which above we highlighted in green. We're going to substitute x equals a tan theta. In this case, a is 2, the square root of 4, tan theta. So we find dx. Now we draw a right triangle with our acute angle theta. Since we have tan theta is equal to x over 2 from here, we have opposite over adjacent. And then we can use the Pythagorean theorem to get the hypotenuse, which will be the square root of x squared plus 4. Since the square root of x squared plus 4 is an expression in our integrand, we're going to go ahead and rewrite that in terms of a trig function. And so noticing that the square root x squared plus 4 is the hypotenuse, and we have 2 as an adjacent side, that means that the cosine of theta is equal to 2 over the square root of x squared plus 4, which means secant theta is equal to the reciprocal. And if we multiply both sides by 2, we have the square root of x squared plus 4 is equal to 2 secant theta. Next, we'll change our limits of integration. When x is equal to 2, we're going to plug that in here and see that we have 2 equals 2 tan theta. That means that tan theta is equal to 1, and that's going to happen when theta is equal to pi over 4. Similarly, when x is 0, theta is going to be 0. So now substituting, we have the integral from 0 to pi over 4. X cubed, we're going to take this quantity here and cube it. So we're going to get 8 tan cubed theta. We have the square root of x squared plus 4, which is right there, to secant theta. And then finally, we have our dx, which is right here, to secant squared theta d theta. So now we're left with this trigonometric integral. Let's go ahead and take all the constants out. 8 times 2 times 2, that gives us a 32 on the outside. We have the integral from 0 to pi over 4. If you notice, we have a tan cubed and we have a secant cubed. So I'm going to go ahead and rewrite this as tan squared theta times secant squared theta. And then in back, we have a secant theta tan theta. And you recognize this back piece here as the derivative of secant. So I'm hoping to do a u substitution for secant. So let's go ahead and replace our tan squared using the Pythagorean identity. Tan squared is equal to secant squared minus 1. We'll let u equal secant theta. That means du is equal to secant theta tan theta d theta. We're going to change the limits of integration again. When theta equals pi over 4, u is equal to the secant of pi over 4, which is equal to the square root of 2. And when theta equals 0, u is equal to secant of 0, which is 1. So our integral becomes 32 times the integral from 1 to root 2. We're going to replace our secants with u, so we have u squared minus 1 times u. And then our secant theta, tan theta, d theta becomes du. And now we have a relatively straightforward integral. We end up with 1/5 u to the 5th minus 1/3 u to the 3rd evaluated from 1 to root 2, which gives us something like this. Now you'll go ahead and do number 4. You'll notice that in the square root, again, we have the variable squared plus a constant squared. So start off just as we did in number 3, let x equals, in this case, a is going to be the square root of 3 tangent theta. And follow pretty much the same steps as we did in number 3. Number 5, the integral from root 2 to 2 of 1 over y to the 3rd times the square root of y squared minus 1 dy. Here, you'll notice that we have our variable squared minus a constant squared. And from what we saw above, we substituted the variable equal to a, which in this case is 1, secant theta. Find dy. Again, we'll draw a right triangle with the acute angle theta. Since secant theta is equal to y, that means that cosine theta is equal to 1 over y. So we have an adjacent side of 1, hypotenuse of y, and then we can use the Pythagorean theorem to get root y squared minus 1. We notice that we can rewrite the square root of y squared minus 1 as simply tan theta, because the tangent of theta is going to be opposite over adjacent. And we need to change the limits of integration. When y equals 2, well, that means that we have a 2 here, and we know the cosine theta equals a half when theta is equal to pi over 3. And when y equals root 2, that means cosine theta is 1 over root 2, also known as root 2 over 2. That means that theta is pi over 4. And now we're ready to do our substitution. So we have the integral from pi over 4 to pi over 3. Our dy is going to be secant theta, tan theta, d theta. And in the bottom, we have y to the 3rd, which is secant cubed theta. And then our square root of y squared minus 1, we saw that that was tan theta. And now we can go ahead and simplify this. Secants and tangents cancel to leave us with 1 over secant squared, which is the same as cosine squared theta d theta. We'll evaluate this using the power reduction formula. 1/2, 1 plus cosine 2 theta going to give us theta plus 1/2 sine 2 theta, evaluated from pi over 4 to pi over 3. So we have pi over 3 plus 1/2 the sine of 2 times pi over 3, which will be 2 pi over 3, minus pi over 4 minus 1/2 the sine of 2 times pi over 4, which is pi over 2. So we have pi over 3 plus 1/2. The sine of 2 pi over 3 is root 3 over 2. And the sine of pi over 2 is 1. So we get pi over 6 plus root 3 over 8 minus pi over 8 minus 1/4. Pi over 6 minus pi over 8 will give us pi over 24. We have our plus root 3 over 8 minus 1/4. We could combine the 3 fractions, but we'll leave it at that for now. Now you'll go ahead and do number 6. Notice again that inside the square root, you have a variable squared here minus a constant squared. So we're going to do another substitution involving secant. But before we do that, notice that you have this 9x squared. So let's start off by letting u equal 3x. So du is equal to 3 dx, which means that 1/3 du is equal to dx. And here we have that 1/3 u is equal to x. So we can rewrite this integral, putting the 1/3 in front. We have our du in back. And we end up with, under the root, u squared minus 4. And in the denominator, we have 1/3 u. The 1/3s cancel. And we now have u squared minus 4 over u du. Now you're ready to let u equal secant theta. Now you can just follow the steps from above. Number 7, x squared over the quantity a squared minus x squared to the 3/2 power dx. First, we look inside the parentheses down here, and we notice that we have a constant squared, a squared minus the variable squared, x squared. So that means that we can let x equal a sine theta. Find dx. Now we'll draw our right triangle. From here, we have that sine theta is equal to x over a. So we have an x here and an a there, opposite over hypotenuse. And then down here, we'll get the square root of a squared minus x squared from the Pythagorean theorem. Now, that expression, a squared minus x squared, we want to write that in terms of theta. So if we look here, we notice that the cosine of theta is equal to the adjacent leg over the hypotenuse. So we have that the square root a squared minus x squared is equal to a cosine theta. So now we're ready to make our substitutions. In the numerator, we notice that we have x squared, which means we'll be squaring this here. Then we have our dx, which is right there. And all of this is being divided by this quantity to the 3rd power, right? We've got the a squared minus x squared in a square root like this, and all that is being raised to the 3rd power in the denominator. So we're going to have a cubed cosine cubed theta. Now we'll simplify this down. The a's cancel. 1 cosine cancels, and we end up with sine squared theta over cosine squared theta, d theta, which will be the integral of tan squared theta d theta. Now we rewrite this using the appropriate Pythagorean identity. Tan squared is equal to secant squared minus 1. The antiderivative of secant squared is tangent. And then the antiderivative of 1 is theta plus c. Now we have to rewrite this expression in terms of x's. So if we look back at our triangle, the tangent of theta in the triangle is opposite over adjacent. And if we look at theta, right, we need to replace this in terms of x's. So we notice that sine theta is equal to x over a. That means that theta is equal to sine inverse of x over a. So we end up with this. Go ahead and do number 8. Number 9, the integral from 0 to 3 dx over the square root of 9 plus x squared. And we notice right in here, we have a constant squared plus our variable squared. So we're going to let x equal 3 tan theta. Find dx. Now we'll draw our triangle with the acute angle theta. Tangent of theta from here is going to be x over 3. So that's opposite over adjacent. And we can use the Pythagorean theorem to get the square root of 9x squared for the hypotenuse. Now, one thing we want to be able to do is rewrite the square root in the bottom in terms of thetas. So if you notice, we can take the cosine of theta, and that's going to give us the adjacent leg over the hypotenuse, which means that the square root of 9 plus x squared is equal to 3 over cosine theta. And this, of course, is the same as 3 secant theta. So the square root of 9 plus x squared is equal to 3 secant theta. The last thing we need to do before we rewrite our integral is to change the limits of integration. So when x is equal to 3, that means we're going to plug a 3 in right there. So we have 3 equals 3 tan theta. That means tan theta is equal to 1, so theta is equal to pi over 4. And when x is 0, we're going to have 0 equals 3 tan theta. Tan theta is equal to 0 when theta is equal to 0. And now we're ready to rewrite our integral. So we're going to have the integral from 0 to pi over 4. In the numerator, dx becomes 3 secant squared theta d theta. And in the denominator, our square root of 9 plus x squared becomes 3 secant theta. Simplifying, we just need to integrate from 0 to pi over 4, secant theta d theta. This is a memorized basic integration formula. We have the ln of the absolute value of the secant of pi over 4 plus the tangent of pi over 4 minus the ln of the secant of 0 plus the tangent of 0. Secant of pi over 4 is root 2. Tangent of pi over 4 is 1. And because that sum is positive, we don't need our absolute values anymore. So I'll just go ahead and put parentheses here. Minus ln of secant of 0 is 1. And of course, tan 0 is 0. So the ln of 1 is 0. So we end up with just the ln of root 2 plus. Now you'll go ahead and do number 10 on your own. Again, notice what we have inside the root. We have a constant squared, right? 2 squared. And then we have this quantity, which is really 3x quantity squared. So I like to start this with a u substitution. Let u equal 3x. That means du is equal to 3 dx. Noticing that we have an x cubed there, if I multiply both sides here by a third, and then raise both sides to the third power, I'll have 1 over 27 u to the third is equal to x to the third. And here, of course, we have 1/3 du is equal to dx. And then changing the limits of integration, when x is equal to 2/3, u is going to be 2. And when x is equal to 0, u is 0. So our integral becomes 1/3, 1 over 27 u to the third, the square root of 4 minus u squared du. That gives us 1 over 81, integral from 0 to 2 of u to the third, the integral of 4 minus u squared du. There's more than one way of proceeding from here. You go ahead and figure out what works best for you. Number 11, the integral of the square root of 2x minus x squared dx. This one's a little tricky to get started if you haven't seen this before. If we were to try a u sub, we get stuck immediately because we don't have a factor that looks like this anywhere outside the root, right? So what we're going to do is we're going to manipulate the inside of the square root in such a way so we can get one of the forms that's going to allow us to use a trigonometric substitution. In other words, a squared minus u squared, or a squared plus u squared, or u squared minus a squared, right? So to do this, let's start off by thinking about how we can turn this inside into a quantity squared plus or minus a constant squared. So if I take 2x minus x squared off to the side and maybe rewrite it this way, and then notice that I could factor out a negative like this, we can complete the square on that. In other words, we can rewrite this in such a way that allows us to simply write x minus 1 quantity squared. Of course, we have that negative in front, but before I can do that, I just added this 1 to my x squared minus 2x. And actually what I really did is I subtracted a 1, because if you distribute that negative, we've really subtracted a 1. So to balance that out, I'm going to add a 1 back here. Okay, now you can pause the video and you can distribute the negative and you can combine like terms and you'll see it takes you back to where we started. So now we've got a 1 sitting in front there. And if I go ahead and put that into our square root and rewrite it this way, 1 minus the quantity x minus 1 squared dx. Now we have u equal x minus 1. So du is equal to dx. And we now have the integral of 1 minus u squared du. At this point, we can let u equal sine theta, du is equal to cosine theta d theta, and you're ready to proceed with the trigonometric substitution. Go ahead and finish this one on your own. Number 12, the integral of 1 over the square root of 9x squared plus 6x minus 8 dx. So this one we're going to deal with very similarly to what we did in number 11. Start off by focusing here and see if you can complete the square on just that. In other words, add and subtract just the right amount so you can turn that part in yellow into a quantity squared. Once you've done that, then you'll do a quick u sub. And once you've done that, you'll be ready for your trig sub.